It's tough to hit that record button when I look over. I'm like, I've been muted for a half hour. Okay. Okay, well, 12:30 at night, looking around. Okay, let's make this short and sweet. There are spheres that are like I've been talking about with regard to the sphere of Hawaii forming that are called Meraki right here. Here's some others. Sorry for the abrupt rushedness through. These, here's some. This one's got a band around it, which I found interesting. I'll show where I got these from YouTube just by searching for Meraki, really. Meraki Boulder and watching all of them. That's concretion, so like there's fractures in it that then have a like fluid transport minerals that then solidify as a concrete between to like heal the rock. And sometimes they'll have it like on each side, like there was maybe even like a fault line kind of thing going on where a current went along one way and another. I was thinking, I don't know. The way it's split in half practically made me think that, though. Like here, it's like, huh. Well, this one's totally different. I didn't know what to make of it. May just be really eroded down, but it looks so different. I don't know if that's on it. I think that the black is actually might be stuff, living things. I don't know what the names are on it. And that, like, whoa. Broken chunks. So this is pretty much how I see like Hawaii. Literally was a sphere that was rolling. I know how ridiculous it sounds, but like, and then broke apart, and the base of the spheres is now resting on the preformed ocean bed that was still cooling, that it's now attached to pretty much and resting in, so that like this structure's like within it kind of thing. And up here is like a certain island. Right here, there's some islands. Literally of that nature. It's just that it's just that cool. It's just that cool. These are different locations, so those were called the Moakai, which formed at 66 million years. Let's see if I can find it. I'm not sure. I'm not sure if this is a paper. Here we go. Treasured spheres protecting New Zealand's heritage of spherical concretions. The Hokianda shorelines are perhaps the richest examples in Northland of these late Cretaceous spherical concretions that weather out of the Punakatir sandstone but other small pockets occur scattered around the north as far south as Silverdale. So these formed 66 million years. There's somewhere I found a paper that was basically saying the Turian, this one, and I looked it up, and that is 66 million exactly. So it's happening while Chicxulub is the impact is like the only thing that's supposed to be really of significance going on in the world at 66 million, and also Deccan Traps. But like, there's a lot going on at 66 million that I've been talking about in my past recent videos because it's a lot going on to the point where it's like, so we going with that impact thing still or what? So, unfortunately, I recorded for a half hour, and this is a 6-minute supplement of what I recorded mostly. Here, these are another one. This one's really interesting because it basically forms like a mudstone and then a sandstone concretion within a mudstone matrix. So there's like a soft material, a solid dense material, and then a soft material at the nucleus. So, and then it splits literally in half, and the soft material just becomes this pile of sand. So cool. They tend to fracture like around midpoint, split in straight segments. These ones, at least, they didn't all seem to, like the Moeraki, these ones. The same guy out there learning. Pardon me, sir. Just a smooth one. I just feel bad playing people's content, so I'm just kind of skipping to video or to the actual images. Even here, we can even see two currents, and what's really interesting there, it looks like it either collides, or it splits, and one goes this way and one goes this way. Or maybe it converges. Oh my god, to see like more currents to get a better idea of what's actually happening. The potential, like maybe the currents then flow in there at some point, like, or out of here and then this way. Then maybe this way. Oh. Like something currents E. Feynman diagrammy? I don't know. I don't know enough. Oops. And then it forms layers and then fills in the layers, I guess. Or actually, that like overlays it. It's almost like it fills in so much that it begins to overlay. I'm not sure. But so then I was looking at this. Basically, the Chicxulub 65. Asteroids and Dinosaurs, Unexpected Twist in an Unfinished Story. Walter Alvarez, an American geologist, was working with other scientists to look for certain rock patterns that would help to explain part of Earth's history. He examined rocks of the mountains in Italy. As he explored, he kept finding an unusual layer of clay that marked the 65 million-year-old boundary between the Cretaceous and Tertiary periods, referred to as the KT boundary. He noted that there were many different sorts. I feel like I'm just reading this. It's almost like plagiarism to just sit here and read it. I really want to jump to here. Pardon me. So there's basically they found father son. Wait, what? Father son Alvarez, geologist and a physicist. His father. So the son Walter Alvarez and father Luis Alvarez, son geologist, father physicist, suggested using a chemical element called beryllium. I'm like, oh my god, it's been so long since I looked at elements. Chemistry is just god. Like the specific names. The more beryllium in the clay layer, the longer it must have taken for the layer to be deposited on dead end. Lewis suggested trying another element, which acts as a timer, iridium. Iridium is often found in meteorites, and meteorite dust rains down on Earth's surface at a slow but constant rate. Wow. So then they recruited scientists to help them find the iridium layer, or iridium in the clay, and found it. What could have caused this spike in iridium? So began digging through published studies to find the location of other KT boundary rock layers. Big spike in iridium was there too. I wonder, there's probably a higher amount of like just thickness of the KT boundary centered in the Pacific region. That's explained maybe by the proximity of Chicxulub. But I don't know if that's a thing. Maybe not, though. Maybe not. I don't want to say that. Like, it could be more like layered of like variants of like dense and subtle, like the mudstone and the concretion. So whatever happened at the end of the Cretaceous must have been widespread. What could have happened to cause these sky-high iridium levels? It turned out that almost 10 years earlier, so someone else proposed, I need to find that paper, had caused the extinction, a supernova. Since supernovas throw off heavy elements like iridium, the Alvarez discovery seemed to support this hypothesis. To further test the supernova hypothesis, the team needed other lines of evidence. Alvarez realized that if a supernova had occurred, they should find other heavy elements like plutonium at the KT boundary. And then at first, the team thought they had found the plutonium, which I really find that interesting that they in any way got a result, such a positive result, but then like after double checking had been contaminated, no plutonium after all. I don't know how thoroughly this was looked into. What could explain these differences? And I was thinking, because I've essentially been saying a sphere or supernova, and literally, it was resting or somewhere around here, probably. That was really here at the time, which was actually all the way adjacent to here before the ocean floor spread, because 66 million years, the pre-expansion Earth, basically, because the Earth was expanding is what was actually happening, and it doesn't function under plate tectonics. All the ocean floor was being added in the basically the 66, like, so light green through here, so like all this was added. So like right around here, a supernova occurred of a particle that was relatively large compared to like boulders on Earth. It was like a microcontinent, maybe something large, like a mini planet that exploded from the currents pressing on it, and then maybe the currents like turning off enough where it just exploded in the lower pressure environment and it caused the Earth to rapidly expand. I don't know if that's part of it, but like then the Earth started to rapidly expand from that time on, which made the mean oceanic crustal age, average age of the oceanic crust, 64.2 million years, slightly older than previous estimates. Basically pushing back to that 66 million a little after, because that's when rapid expansion started to happen everywhere. Like the supernova of this particle, which it was a supernova, just of a small scale system that relative to a star wasn't like quite the same, but it's equivalent. This system's equivalent across scale, which Earth itself was doing. Its expansion process was itself supernovaing. Okay, so I was looking around to see if there's any evidence of plutonium 244 that's emerged maybe in the meantime or at all. I don't know when this is written. It may be a topic that dates back to like looking for a supernova. Agreement is now extant. Let's just read it up here, I guess. Precambrian Bastnaesites by D.C. Hoffman et al. In 1971 was explained by one of the authors in 1974 as due to possible inflow to the Earth as a cosmic dust component from supernova remnants, not as due to survival of the primeval plutonium-244 nor to cosmic ray component. A search for the live quote unquote plutonium-244 has recently been started with a 80 kilogram of wet sediment from 5,800 meter depth off Hawaii to see if the inflow of the extra solar system material in a preliminary to see the inflow of the extra solar system material and a preliminary result on alpha counting for plutonium-244 separated from a small portion corresponding to 400 grams of the sample indicates an upper limit that is comparable to the expected amount of plutonium-244 in deep sea sediment. Influence cosmic. It's hard to read this, especially when I don't even know if I can find any more of its. Oh, Australia. That's a good. As soon as I see Australia, I'm like, it's a good place for this to be talking about it. Millions. Oh. They say it was made in colliding stars and later rained down through Earth's atmosphere. Few atoms on Earth can help us learn about where half of all. Here we go. Here we go. Here we go now. Is the last of 94 atoms characterized as naturally occurring. So it really is like the top of what a system would produce. So that it's like a micro supernova, basically, of this mini system on the Earth's surface that really was large, but still like wasn't a star. Maybe it just didn't produce it. But I don't know if that makes sense. It probably would. It probably would produce it. Like it's more likely that we're gonna find it sooner or later in looking around for it. Signal. I already requested it. Heliospherical compression. This would be hilarious if the supernova of the system influenced. Okay, that says PDF. Come on. Just give me the virus, apparently. I don't know. Check access. Dude's killing me. Two distinct influxes of iron in the last 10 million years, accompanying low quantities of plutonium. Influx ratios are similar for both events. Mergers of neutron stars. Let's see. I'm just thinking maybe it's like delayed, especially with the iron. Because essentially it's a rapid expansion of the earth where maybe I don't know how it'd be delayed that much where it's not like 60 million. To be 25 million seems really delayed to be still related to the 65 million-ish supernova. No, Cretaceous. I don't want to search for 66. Okay, I can see. I just don't want to make it make noise. Bing. Oh. Large samples used in this work were taken from one part of the crust and from the bottom. So this is from taking samples from then. Let's check it out. Oh, it's just there. That looks cool. Like, that looks real cool. Iron manganese crust. 25 centimeters. Okay. That one's too specific now. So I forgot what I talked about already, because I recorded a half hour, and now I'm back to about a half hour. Plutonium-244 geology. I'm just wondering if people who are not aware or looking for the supernova aspects of the 66 million radiometric dating kind of time frame come across the data and just describe it in detail, but don't necessarily mention that the supernova aspect of the Chicxulub time frame. I don't know how they would possibly not make that connection. It seems like that's probably something that's somewhat known. Plutonium fission xenon is absent in lunar finds, while carbonaceous chondrites contain the so-called xenon HL, which is a strange fission-like xenon component whose isotopic composition is different from that of the plutonium fission xenon. Re-examination of a vast amount of existing xenon isotope data reveals, however, that lunar fines and carbonaceous chondrites both contain appreciable amounts of plutonium fission xenon, and they began to retain their xenon almost 5.1 billion years ago. Present paper re-examination of the experimental data is extended to the lead, and potassium argon dating methods. Okay. I'm a little sad. I didn't record my first. It's almost like it's obviously I should just stop. Feeling kind of like I don't even want to do this anymore. It's just a fucking... It kills me. That's probably the truth. Page not found. Page not found. Page not found. Trans-uranium elements were synthesized by the R process in exploding stars. There remains, however, uncertainties concerning... Okay. Frick. I don't know if I... It's really disappointing to have realized I was muted. I clicked it, I was like, I remember doing it. This is before I was even recording. Whoa, those are not... Those look more like Trovants. I don't think that's Meraki. Oh, that's just concretions. Just wonder if they're like energetically connected and before it eroded away. Some intermediary region. How cool. And then this, it just looks surreal. New Zealand. I don't even think that's Meraki. Whoa. Incredible. It's got a little bar across it, like an eyeball shape. Oh, pardon me. A little Jupiter or something. A red spot maybe on Jupiter even, like both. I don't know. These are cool. Sorry if I'm skipping by anything. Anyone's like, I want to see that one. No one watches my videos, so I don't know. Sooner or later, people will maybe feel that way, and I'll be like, oh, sorry about that, but, concretion geology. Whoa. Whoa. Just looking at concretions. La la la. That's pretty cool. Kansas. Oh. Bunch of little blobs inside make me think of like a nucleus, like a protons, neutrons, some something of that nature. Not at all. Sorry, I know I'm just kind of looking at this stuff now. I'm just a little down. Sombrero Rock. Whoa. Cool. What the? It's sideways? Oh my god. Sombrero Rocket League. No one? No one? No one? can't be in Florida. Oh no, where was that? There. Patagonia. Oh my god, how incredible. Why is there nothing on YouTube? Argentina. Oh, what? Oh, down here. Wow. Theodore Roosevelt Monument, or National Park, North Dakota. Whoa. Let's see. Maybe if I add geology before I move on. Increation.
Places that already have recent graffiti on them. Why can't I just add to that? Cannonball concretions, like we see here, are a geologic anomaly. They are beautiful by themselves, and they don't need our help to make them any more so. Unfortunately, this is one of the graffiti hotspots in the park. The sandstone in the Badlands is very soft and naturally erodes. If you add to that erosion by carving your name to it, you are speeding the process. If every visitor added graffiti to that cannonball, 100 years down the road, it could no longer be here. You have added to the destruction of a unique feature at Theodore Roosevelt National Park. The National Park Service mission statement is to preserve unimpaired.
It's just fucking talking about. I can't rely on the government to give us useful information, no offense. Just fucking. Don't graffiti. Okay, let's just say. I just assume people are annoyed. Yeah. Oh my god, like the flows. I don't know what to make of it, but there's probably something. Something. Incredible. Like, what happened here? Okay, this is underlying this. Graffiti is fair, but it's just like that's too bad. That is too bad. Ooh.
So, if you remember a while back,
Pardon me, sir. Pardon me, sir. We got.
some of this stuff is a lot softer than the rest of the material. Use it rather than bust up. So let's go ahead and get moving stuff. So I thought I was recording. I guess I wasn't. So basically, what happened was, rather than bust up the dolly to move this, make it easier for transport, is to use a hammer and chisel. The chisel's right there, because in here, that some of this stuff is a lot softer than the rest of the material is. But now I've got it broken in half, we're gonna move it to the concrete. Around like that. Now I would use this one for this part, it'll make more of a mess. So at least want to get started with this. Just from hitting it where I have been, there's a crack. Now we got a crack forming. It's just from hitting it
That shape there.
where I have been. There's a crack to form. So I'm not gonna get a even cut through, but it's still gonna look cool.
Okay, here we go. You got it. Ooh. He's got
Who knows how long? And we're gonna be the first ones.
Who knows how long? Oh my god.
So it looks like just a bunch of shells. And it's still pretty cool.
what to make of stuff like that.
These days I'll get like a fossil or like a bone or something. But it's still kind of cool to see the different shells that are on the inside. Get these out of the way. Cool. We're shipping with so much. I could do a giveaway for one of these. Or a giveaway both of them. So.
The way it did that. Oh man. He's going right down the middle too. It's like, nah, I'm breaking a 120-degree angle right here. Oh my god. Splits one particle in half, but then at the next particle it does not split in half, it goes around it. 120. Maybe.
One separate concretion. So, let's go ahead and show off what's on the inside of this one first. Breathing too heavily here. Shaky camera. Okay. Alright. You have not, no one's seen the inside of this? Ever. So we got some more shells. Sweet. Nothing too crazy. But I can see that a couple good whacks right here will break off this other side. And I'll free this other concretion. So let's go ahead and do that. No. Free this other concretion. So let's go ahead and do that. So let's go ahead and do that.
Let's see. Oh. I wonder if it broke off pretty good at. Oh. It's like a bond. Like a node. I don't know.
That's got a lot of shells in it.
Wishful thinking.
Alright, let's do this last one here. Alright, let's see what we got. You guys ready? Here we go.
This is pretty. I should watch more breaking rocks open videos.
Nice. That's kind of an interesting shape. Yeah, it's kind of cool. All these different shells. Let me get these on top of the table and we'll do a close-up shot. Alrighty, so we got them all on the table here. The big one, the second one we broke open, and then number 3 there. This is what we got on the inside. Always really cool shells. Now, one thing I've always wanted to find is a crab concretion, but I'm not that lucky. But this is still pretty cool to see all the different shells. And like I said, if it wasn't so expensive to ship this stuff, because this would be very heavy and very expensive to ship, I would give some away. But again, it's too expensive, so I'm not going to worry about it. But it is kind of cool. You can kind of see down here. This is kind of was the dividing part between this one and this one. It's very soft sand. So the fact that it didn't break during transport from being one big piece, a couple pieces,
Crazy.
is surprising me a little bit. But yeah, here's the other one. And it's kind of cool. Look at that little shell. Look at that little shell right there. It's so little. This is pretty neat. Let me know what you think. I'm not good with shell identification, but it's just cool. Yeah, that was fun. Glad I didn't wait.
Breaking rocks open. Breaking rocks open. Oh my god. Okay. See y'all in the next one.